In this video, we're going to study an algorithm for solving the flow assignment problem. This algorithm was published in 1956 by Lester Ford and Delbert Fulkerson while they were working at the Rand Corporation. This is the same Ford who came up with the Bellman-Ford algorithm for shortest paths, by the way. If you haven't watched the previous video where we set up the flow assignment problem, it's a good idea to watch that first. Let's set out formally the problem that we're trying to solve. We're given a network with capacities and we want to construct a flow. Pause, read these definitions and then copy them out so that your hand muscles remember them, not just your brain, and then I'll make some comments. First comment. The definition of a flow says that the total flow in should be equal to the total flow out at all intermediate vertices in the network. It's worth just doing a sanity check. Let's take node V for example. Total flow in is 3 plus 3 equals 6. Total flow out is 2 plus 4 equals 6. Right, that works. This basically says stuff isn't allowed to accumulate anywhere in the network. Here are two ways that we could write this constraint out formally. These equations just say in symbols that the total flow out of V is equal to the total flow into V, or in other words, the net flow into V is 0. This is called flow conservation. It's important to be able to express ourselves symbolically, to cross the bridge from words to formal symbol manipulation, because otherwise when we come to try and write out proofs, the words turn out tongue-twisty and muddled. So you really should get into the practice of writing out this sort of equation. The idea isn't just that you should remember it or be able to understand it. The idea is that when you want to express a wordy idea properly, that you should have the symbolic skills to be able to do so. Anyway, moving on. Flow conservation is required to hold at all vertices V except for the source and the sink. That's because there's a net flow out of the source and a net flow into the sink. In this network, the net flow into the sink is 9 plus 4 equals 13. And the net flow out of the source is 12 plus 3 minus 2, which again is 13. This amount is called the flow value. Remember, when you're computing the flow value, that you don't just add up the outgoing flows from the source, you have to subtract the incoming flows. In other words, you have to compute the net flow. Pause the video and have a go at defining the flow value using symbols. This is what you should have come up with. Now, here's an interesting exercise. It claims here that the net flow out of the source is equal to the net flow into the sink. It makes intuitive sense that this has to be true. I mean, where else could the flow go? But how should we prove it? That's actually left as an exercise, and I hope it'll be clear how to prove it after you've watched the next video. Anyway, the reason I'm banging on about all this symbol pushing is because unless we can state exactly what it is we want to achieve, namely finding a value f on each edge that satisfies all these equations, we can't even begin to argue that our algorithm does what we want. And so what is it that we want? We want to find a flow with the maximum possible value. I posed a question on the previous video, and if you haven't tried to answer it yet, then you should try now. Can you find a way to increase the value of the flow shown here by adjusting the flows on some of the edges? Pause the video and try to solve this, because once you see the solution, you'll be most of the way to a complete working algorithm, and it's always so much easier to understand an algorithm when you've come up with it yourself. Here is a procedure for increasing flow. I want you to imagine that you're in Bandit country, and you're a bandit, and the multinational oil corporation has built a pipeline network, and you want to sneak into the switching stations and adjust their controls so that you and your fellow bandits can siphon out oil at other points in the network. Let's work through an example. I've changed this example from the previous network. I'm going to illustrate the procedure for this flow here and then leave it for you to apply it to the earlier flow so that you can check your answer. Okay. First, we have a bandit at vertex S, the source. This bandit can sneak into the source vertex and adjust the flow values and siphon off some of the flow. Okay, so now there's a fellow bandit at vertex B who calls out to the first bandit, "Hey, send some of your excess down the SB pipe to me so that I can have some too." The S bandit adjusts the valves at S, the B bandit adjusts the valves at B, and is thus able to siphon off some of the oil. In fact, the whole country is swarming with bandits. There's one at vertex C too, and the C bandit sees that the B bandit has some oil to spare and calls out, "Hey, adjust your valves and send some of your excess to me." Okay, so we can siphon off oil at S and at B and at C. What about A? That one's harder, but luckily the bandit at A is sharp-witted. This bandit calls out to B, "Hey, here's a cunning plan. You know how to get excess oil at B. How about I take a little bit from the A to B flow and you make up for it by sending some of your excess on to T. That way the oil company will still be getting just as much as before, so they won't sound the alarm and call in the police." Okay, so that's the plan. It means that we've figured out a scheme to be able to siphon off some excess at A. And then there's a slightly dim-witted bandit at T who calls out to A and asks for some of that excess. I say dim-witted because the oil executive has been spying, and this dim-witted bandit has alerted the executive to the fact that more oil can be sent to the sink. So, what does the oil executive do? Well, they just replay the thinking that led to reaching the sink. First, we know we can extract flow at B, and in fact the amount we can extract is 3. Because we can extract flow at B, therefore we can extract flow at A using the redirection trick. In other words, instead of extracting flow 3 at B, we could extract flow 3 at A. The thing to pay attention to here is that we're not just naively adding flow. This particular step involved removing flow along an edge, or if you like, adding negative flow. Okay, final step. Because we can extract flow at A, therefore we can extract flow at the sink, T. We can send an extra 2 units of flow down the A to T pipe. Now, we have 3 units available at A, and we can only squeeze in 2 of those units going to T, and the oil executive doesn't want to waste anything, so this is what to do. We'll only send 2 from the source to B, and we'll only reduce A to B by 2, and we'll send 2 from A to T. It's worth thinking very carefully about this change. In particular, let's think about flow conservation. Let's take vertex B for example. Previously, the total flow in was 4 and the total flow out was 4, so the flow conservation equation was satisfied. Now, with these changes, the total flow in is 2 plus 2 and the total flow out is still 4, so flow conservation is still satisfied. And we can go through all of the vertices like this and all the changes that the oil executive wants to make and convince ourselves that in every case we leave the flow conservation equation still satisfied. So, after this round of adjustments we have a new flow. It's a valid flow because our adjustments were made carefully so that we still satisfy the equations that define flow, and in this case we increase the flow value by 2. And that is how the Ford-Fulkerson algorithm works. I'll leave you to read through these steps to yourself. This is just a bit too hand-wavy a description. To actually turn this into code, let's try to think more algorithmically and say exactly what's going on in steps 2 and 3. We'll start with step 2, running the Bandit search procedure and finding a sequence of edges on which to adjust the flow. Remember what the Bandits did. They stood at opposite ends of an edge, and one of them shouted to the other, "Hey, you have some excess. Let's find a way for me to have some too." Let's make this explicit. What we'll do is we will construct a new graph. This graph is referred to as the residual graph. It has exactly the same vertices as our original graph, but it has different edges. It has 2 types of edges. Have a read. So what are we doing here? Well, these 2 clauses correspond exactly to the 2 types of action that the Bandits could take. Let's take vertices S and B, for example. The Bandit at B shouts to the one at S, saying, "You could send me some more flow," and that's what the blue S to B edge represents. Or let's take vertices A and B as the other example. The Bandit at A shouts to the one at B, saying, "You could tweak the valves at your end, and I'll reduce the flow being sent to you, and that way I get more." This adjustment is labelled on the residual graph as an edge from B to A, labelled decrease the A to B flow. This isn't a typo, by the way. We really do mean there's an edge in one direction saying to decrease the flow in the other direction. Okay, so this is the residual graph. The next thing we do is we find an appropriate sequence of edges on which to update flow. In other words, we find a path from S to T in the residual graph. Such a path is called an augmenting path. The last step is for the oil executive to adjust the flow along all the edges of this path. We scan through all these edges in the graph and ask, by how much can we change the flow? On edge S to B, we could increase by up to 3. On B to A, we could apply a decrease of up to 3. And on A to T, we could apply an increase of up to 2. So the limiting edge here is the A to T edge, 2. So we apply a change of 2 along each of the edges. Now, here's a lemma. Pause and read it. This lemma says that what we have after updating the flow is another valid flow. What does this mean? Look back at the definition of flow that you copied out right at the beginning of this video. For a flow to be valid, it has to satisfy 2 things. First, it has to be between 0 and capacity on every edge. Second, it has to satisfy flow conservation at every vertex, apart from the source and sink. You should be able to persuade yourself of the first property fairly easily, that this update still leaves the flows between 0 and capacity on each edge, because that's just how we chose the update amount delta. And the second claim, the claim that flow conservation is still satisfied? Look very carefully at the types of changes we've made. Look at vertex B, for example. The change in the total flow coming in is +2 -2, which is 0, and the change in the total flow going out is 0, so the net flow is unchanged. And take vertex A, for example. The change in the total flow coming in is 0, and the change in the total flow going out is +2 -2, which is 0. So again, the net flow is unchanged. You should sketch out for yourself all of the 4 possible configurations of how flow at a vertex might be changed, the 2 we see here plus the 2 others, and you should persuade yourself that in all 4 cases the net flow at a vertex is unchanged. And just the same sort of thinking should persuade you that whether the first edge of our augmenting path is an increase edge or a decrease edge, then the value of the flow, i.e. the net flow out of the source, has increased by delta. Now, I'd just like to go back to the example that we looked at earlier in this video. Can you find a way to increase the value of the flow shown here? I hope you tried it yourself back then, and now I'd like you to have another go, this time using the algorithm that we've just discussed. Pause the video and run the algorithm. This is the residual graph you should have drawn and the augmenting path, and you should have ended up producing a flow of value 14. Okay, so that's the algorithm. Let's have a look at it in code and I'll make some comments. First comment. We had to build the residual graph and then find a path in it from the source to the sink. We didn't say how to choose the path, we just said find some path. There are various things you could do here. You could, for example, you could choose the path with the fewest number of edges using breadth first search, or you could find the path that gives you the biggest delta. And these are standard variations of the algorithm that each have their own name and their own inventors. But the big deal here is that find a path in the residual graph is just a plain vanilla pathfinding problem. It doesn't need us to look at the edge labels at all. All of the troublesome stuff about what a flow is and capacity constraints and so on, all of that has completely vanished in this part of the algorithm, and we've reduced the task to something much simpler. Next comment, while true. While loops are big scary things because you always have the sneaking suspicion that there's an infinite loop hiding there to bite you. And in this case, you have every reason to be scared. There are some pathological graphs, very simple graphs. In fact, there's one graph with just 6 nodes where the algorithm does not terminate, and in fact it doesn't even get close to a maximum flow value. But people still use the Ford-Fulkerson algorithm because it seems to work very well in practice, because in common cases it can be proved to terminate. Let's have a look why. Here's a lemma. Pause the video and have a read. Okay, now let's prove this lemma. We're going to go through the code step by step and ask, if all the capacities in our network are integer, can we prove that the flow will always be integer on every edge? First, the initialization. We initialize the flow to 0, which is certainly an integer. Next, the augment. Since capacities are integer, and since the flow we've got so far is integer, then the residual capacity on each of the edges will also be an integer. And so delta, the smallest residual amount among all the edges on the augmenting path, will also be an integer. And hence the new flow values on each edge after the update will still be integer. Next, this assertion here that delta is strictly above 0. Remember, delta is the smallest residual amount on each of the edges along our augmenting path through the residual graph. And we only put edges into the residual graph if there was space to change the flow on that edge, and so delta has to come out non-zero. Therefore, the total flow value increases by at least 1 on each iteration. And so the total number of iterations through the while loop is bounded above by the maximum possible flow value in this graph. We have to increase our flow value by at least 1 every pass. And so this gives us a final answer for running time. Running time is big O of value of the maximum flow times E, where E is the number of edges, because the augmenting path stuff can all be done using breadth first search in big O of E. Just a small aside here, earlier in the course we said that breadth first search takes big O of V plus E, but if we think more carefully about the residual graph, all we actually need to explore in it is the vertices that are reachable from the source, and there are at most E of them, so we can trim this part of the algorithm down to big O of E. Anyway, there are better running times that you could get if you're careful about how you choose the augmenting path, and you can read the accompanying lecture notes for more details on those. Okay, so that's the Ford-Fulkerson algorithm for finding a maximum flow. But wait a moment, it's obvious that we increase the flow value on every loop around the iteration, but why on earth should we trust that this algorithm actually finds the maximum possible flow? It's basically a greedy algorithm, every step just taking a little bit more flow value and not looking at what the consequences might be. And so naturally we've got to wonder, is this algorithm going to paint itself into a corner, or will it truly find the maximum possible flow value, assuming of course that it terminates? In the next video, we're going to look at a proof of correctness for this algorithm. And the proof will rely on one line, this comment here on line 15. Let S be the set of vertices that the bandits can reach. Now there are plenty of textbooks and other YouTube videos that you can find that will tell you all about this algorithm, and they won't even mention the bandit search problem. They just say, here are the rules for constructing the residual graph, and that's it. But in this video, I made a big deal about the bandit search problem. Basically, the bandit search is the big idea, and the residual graph is just an implementation detail. If you're an engineer and you just want an algorithm that works, the residual graph is all you need to know about. But if you're a computer scientist or a mathematician and you want to understand why the algorithm works, or if you want to understand it well enough to be able to invent your own algorithms based on similar ideas, then the bandit search is what you need to be thinking about. Why do I think this? Because the big idea in the proof of correctness is all about the bandit search, and the most elegant algorithms are always those in which every part of the algorithm matches up to key lines of reasoning in an elegant and concise proof.